I would like to compare some different terms which all sound similar and can therefore confuse students. Atomic number is number of protons. Remember, atomic number is linked to elemental type. For example, nitrogen always has 7 for its atomic number. Atomic number is written on the bottom left of an atomic symbol. Mass number is protons plus neutrons. Since isotopes of a particular element have different numbers of neutrons compared to each other, they have different mass numbers. We call it mass number, but it's not exactly how much an atom weighs. Instead, it is counting subatomic particles in the nucleus of a particular atom. Mass number is written in the top left of an atomic symbol. Average atomic mass is something we haven't mentioned yet. It's confusing because it has the word atomic in it and the word mass in it, but it's totally different from atomic number or mass number. Average atomic mass is how much an atom weighs. It is not, however, the kind of average you are used to, where you add all the numbers, then divide by the number of numbers. Instead, it is a weighted average, and is based on how abundant each of the isotopes is. The average atomic mass can be found at the bottom of each square on the periodic table, and will be a decimal value rather than a whole number. We can calculate average atomic mass by finding the sum of the fractional abundances times their isotopic masses. Let's look at boron, for example. It has two main isotopes, boron 10 and boron 11. Boron 10 has a mass of 10.0129 AMU and an abundance of 19.9%. Boron 11 has a mass of 11.0093 AMU and an abundance of 80.1%. Notice that the abundances add up to 100%. This should always be the case. I could have given you just one of the two abundances, and then you could subtract from 100 to find the other one. Our first step would be to take those abundances in percentage form and turn them into decimal form by moving the decimal point over 2 places to the left. We would write 19.9% as 0.199, and we would write 80.1% as 0.801. Those fractional abundances will tell us how much weight to place on each of our masses in our weighted average. The one that's more abundant will count for more in our average, and the one that is less abundant will count for less. We take the abundance of boron 10 in decimal form and multiply it by the mass of boron 10. Then we take the abundance of boron 11 in decimal form and multiply by the mass of boron 11. And then we add the results to get the average atomic mass of boron. We come out with 10.811, which is the number listed in the square for boron on the periodic table. If there were more isotopes, we would include them in our calculation. For each isotope, we would do its fractional abundance times its mass, and then we would add up all of the results at the end. I recommend doing the whole calculation at once in your calculator, using parentheses, so you can avoid rounding error. Always use the full value of the masses given in your calculation. Do not round them. If you end up needing to round at the end, keep the same number of digits as the original masses. The abundances of each isotope can be determined with mass spectrometry. Each isotope would have its own peak in the mass spectrum, due to having different masses. The area under the curve for each peak could be measured, and the relative amounts could be used to find the percent abundances. The natural abundance of copper-63, weighing 62.929599 AMU, is 69.17%, and the natural abundance of copper-65, weighing 64.927793 AMU, is 30.83%. What is the average atomic mass? Is it A, 63.54 AMU, B, 62.93 AMU, C, 64.93 AMU, or D, 127.86 AMU? The correct answer is A, 63.54 AMU. Again, remember this is not a regular average where we would add up the masses and divide by 2. It is a weighted average where we take each mass and multiply it by its fractional abundance and then add them up. There is no division step because we are multiplying by the abundances, which are less than 1. The number we come out with is somewhere between the mass of copper-63 and copper-65, but it is closer to the mass of copper-63 because that isotope is more abundant.